טוב, שלום רבותיי, אנחנו מתחילים את הסמינר הבא שלנו, של החוג להנדסת חשמל ואלקטרוניקה של המרכז האקדמי לב. תודה לפרופסור פלקוביץ' ממכון ויצמן שהסכים לבוא אלינו. אני רואה פה כמה אורחים חשובים, דוקטור קרא איוונוב מחברת מובילאיי, פרופסור עמוס עזריה מאוניברסיטת אריאל, פרופסור אליס לוסקין מאוניברסיטת בר אילן. תודה על הכבוד. אז פרופסור פלקוביץ' הוא, הייתי אומר, אנציקלופדיסט, לפחות זה ככה אני חושב. תיאורטיקאי, עשה תארים באוניברסיטת נובוסיבירסק בברית המועצות, מי שלא יודע, בירה שלישית מדעית של ברית המועצות, ויש אומרים ששנייה, ומשנת 1991 פרופסור פלקוביץ' במכון ויצמן ברחובות, פרופסור פלקוביץ' התחיל מהידרודינמיקה, אחר כך עסק בדברים צמודים או קשורים, כולל גשם ודברים אחרים, אפילו מנועי שריפה פנימית וכו'. ובערך 5 שנים האחרונות, אולי יותר, פרופסור פלקוביץ' עוסק בתורת המידע, וזה הנושא שהוא ידבר איתנו היום. גרגורי, תודה רבה, במה שלך.
אוקיי, תודה על ההזמנה, ואני בדרך כלל מלמד את הקורס הזה במכון כבר משהו כמו 15 שנה, וגם מלמד את זה בחו"ל, אבל תמיד באנגלית. אז אני פשוט ניסיתי כמה פעמים לתת הרצאה בעברית, וזה פחות טוב, בוא נגיד ככה. אני רוצה שזה יהיה ממש ברמה גבוהה, אז כל הסליידים וגם אני אדבר באנגלית, אבל אם מישהו יש איזה בעיה עם טרמינולוגיה או גם עם אז אפשר גם לשאול שאלות בעברית, ואני מאוד מאוד רוצה שזה יהיה מאוד אינטראקטיבי, זאת אומרת, גם אני אשאל שאלות, ואני מקווה לקבל תשובות. אוקיי, אז בואו נעשה את זה באופן אינטראקטיבי, וגם באנגלית, גם בעברית. אבל אני אעשה רוב ההרצאה באנגלית. So this is a popular, not even semi-popular, it's really popular. I tried to make it popular lecture. And there is a book which just came out 2 months ago. This is called Physical Nature of Information at the Princeton University Press, which is a regular course, a graduate course, which I taught here and at Weizmann, at NYU, Harvard, many places. And it's a real course. So if you be interested in any aspect, there is formulas and problems and detailed solution of all problems. What I'll try to do is some kind of a panorama. So I want to give you one message, which is that there is a kind of a new language in which we can tell different stories, which some of them new and some of them old, all we can tell on the same language. And this is a language of information theory. And I'll show a few examples how some old things and some new things are done in this language. And for me, it's very fascinating. I'm a physicist and I'm interested in physics, but I think that physics is essentially is information theory to a large extent. And it took me like 50 years to, I'm not young, to understand this. And I'll try to convey this and maybe at the end. But so I'll briefly remind what is the physics of this. Then I briefly tell what is information theory, really in a very simple, there will be few formulas. And then I'll give few examples, and in the end, maybe we'll go to some kind of freewheeling discussion. So all this is essentially something which looks like not physics, not engineering, not anything. It just, what can we say about something that you don't know? And many things could be actually turned into this problem, even though they don't look like this at the very beginning. So it's at the very beginning, of course, Bereshit, but in the beginning of where the first quantitative measure of how much we can do appeared from a very engineering problem, and the problem was how much you need to burn to move something. And of course, people were doing this for few thousand years. I mean, burning things and turning heat into mechanical work. But it's really when people started to do steam engines, when it was industrial revolution, and it was an industrial scale. And so you start to notice that sometimes you need to pay more to move this to kind of why you need to pay more for coal than for wood, for example, and how much more you need to pay for it. So you need to start asking, what is the efficiency of converting heat into work? It all was a very practical, very engineering problem, and essentially it was about money, and we'll return to money a little bit later. So let's look at it from a very abstract perspective. So what is a heat engine? Heat engine is a simple thing. It's a reservoir at temperature T1 from which you can take some heat, Q1, and then you can use part of it for work, which we call W, and then you lose some part of it, Q2, which goes to some environment or some other, which you call another heat reservoir at a lower temperature T2. So what your work that you can use is the difference between Q1 and Q2, and of course you naturally want this Q2 as little as possible. So you ask, what is essentially is there any bound on Q2? Could I make it very, very small? And the genius in France, Sadi Carnot, answers this question. I've read his notes, they're very interesting. They're wrong. I mean, his arguments were wrong. He believed that heat is conserved separately, but he was a genius, so he got the right answer. And so he actually wrote this formula, that Q2 over T2 must be always exceeding or equal than Q1 over T1. So if T2, Q1, and T1 are all finite, then you cannot make Q2 less than this finite value. That's it. So you always lose some of the money that you pay for your fuel. You always lose. You want to lose less, make your T2 much smaller than T1. And that was essentially, and that explains you why you need to pay more for coal, because it has a temperature of burning higher than for wood, for example. It's was an interesting story. I mean, all his things were burned, and then his brother, because he had typhus, and then his brother 20 years later found one notebook which survived, and that's how we know what actually Sadi Carnot wrote. And some decades later, Helmholtz actually, Kirchhoff actually calls this quantity entropy. Entropy is a very interesting word. It starts like energy, N, and then it has tropos, which is a Greek word for a way or for a change of way. Tropa it's in Russian if someone knows Russian, but tropos, and of course this tropos is a very so this entropy, it was this ratio of Q over T, and it was 50s, about the same year as Darwin published his work. There was a very fantastic decade. Two probably most important things were done by mankind. It's in evolution theory, and then this idea of entropy. So a very abstract idea, which in a moment we'll see how far it's really used, was born from a very engineering need in an industrial revolution, and it was a ratio of something which people empirically knew, which was heat, and something which people empirically knew, which was temperature. Then, and the statement which Carnot actually made to bound the heat engine was a statement that entropy always grows, that Q1 over T1 that you took out will be always less than Q2 over T2 that you get out. And then, of course, the first way to deal with such things, and again, at that point, it was not considered that we are doing something about knowledge or ignorance or whatever. It was very engineering things. But now we look at it and we call the thermodynamic was the first phenomenological way to do with treating unknown. And it has two laws. One law was just formulated by Carnot, its second law, which was entropy growth. And the first law, which actually discovered empirically by Mayer at 40s, Carnot was 20s, Mayer was 40s, 1840s, and then Kirchhoff was 50s. So it was a statement that if you can really know what are the energy state of a system, and then you observe a process in which you do this work, and you find out that they aren't equal to each other, you call this difference heat. It's just a religious statement that we believe in the conservation of energy. It's really important to understand what's going on here, right? Of course, there is all this empirical knowledge that we use because we know what is heat before all the thermodynamic, right? It's something which we have from still. The moment we start to use it as a science, this is a definition. And the moment you start to generalize it, for example, apply it to a stock market, then that would be your visible transaction cost. That's how much money somebody paid to somebody else. And as any energy, it's conserved in a sense that if I get less money in a payment, then there will be more money in the other side. But there are some things which happen outside of my view. It's not necessarily bribes. There are some hidden processes, and that would be called heat. It's a direct analog of heat. So in a sense, already here appeared very important distinction, which Maxwell at 60s very clearly realized, that there is something visible, measurable, and something hidden. And heat is a measure of a hidden part of energy. This was really conceptually very important. And then people started at 60s and 70s try to justify it and see if we really can say, okay, if we don't know about something, maybe we can estimate the probabilities of different things happening and understand what is this entropy is. I mean, what is it related to something? And here two most important formulas. One is this one. It's Boltzmann. It's written on his gravestone in Vienna in the cemetery, which I think is the most important and interesting part of Vienna. There is a Boltzmann grave in a very kind of visible place, and it's written on this grave. S is the logarithm of gamma. It's actually here. So what Boltzmann says that if the system has n states, and we don't know anything about it, and here this word "know" starts to diffuse into all this. But it was all implicit in Boltzmann writing, then entropy is just a logarithm of the number of states. One can say that this is a minus logarithm of a probability of any state, because the probability of any state is 1 over n. So this was the Boltzmann formula. And sometime about maybe 20 years later, the Gibbs formulated in a little bit more general way. He said, but if we know that different states has different probabilities, so this Wi not all equal to 1 over n, then, said Gibbs, what you need to interpret as entropy, which we learn in thermodynamics, is an average logarithm. And since this moment, for last 150 years, we're averaging logarithm. The most of the things that people do in different things is this. I think this is probably the most important gift of physics to the rest of mankind. W logarithm W, this formula. And now I want to show you how it appears in different places and how it's actually from industrial to information revolution and to the present revolution, how it determines many things. So now we see that Boltzmann and Gibbs are different way. One is a more general than another. Boltzmann is a particular case of Gibbs formula when all probabilities are equal. Now, by the way, the book is illustrated. So this is, now I'll try to illustrate with this picture that entropy is not actually the property of a system, is how much we don't know about it. For example, in the previous way, if we don't know these Wi's, we assume that they are all equal, and this is always larger than this. And that eventually lead us to interpret entropy as something about not a system, but something between us and the system. But for this, we need a language, and this language is an information theory, and it's a very simple language. So I'll try to give it a brief introduction. So there are n boxes, more or less like in this Boltzmann system. But let's say there are boxes, and in some of these boxes is a candy hidden, and we want to know in which box. And somebody tells us, in the box number 5, how much information we obtain. Well, it depends on the number of boxes, apparently. If we know from that one that there is a candy, and the candy is 1, and the box is 1 that we don't need any information. If there are 2 boxes, apparently this information must be less than if we have 1,000 boxes. So this information as a function of n must be a monotonically growing function. We are now at 1920s. I mean, I also want you to see historical line, right? So it's just 1920s, even though it was formalized by 40s, in 40s by Shannon, but the formulas actually appeared in 20s. So apparently I of 1 is 0. Now, if I have n times m box, let's say I have n boxes, and each box have n compartments, okay? So apparently I need to get first information in which box, and then information in which compartment. So I would expect that this function of this number of compartments would be dividable into a sum. Now immediately it's clear that it must be a logarithm. If some function of a product is a sum, then this function is a logarithm. Okay? Is that simple? You can say that what is this information? We can take the logarithm under the base 2, and then it would be a kind of yes, no, right, left question. We can say in the right half or in the left half, and we get answer yes. Then we go to the right, and then we divide it again. So this hierarchical subdivision is something which stands behind this logarithmic law, and it's just common sense. And of course, the Shannon in 1949 formalized it very nicely, and now we call it Shannon entropy, of course, is that he say it's essentially a number of questions you need to remove the uncertainty. So amount of information is how much uncertainty you had before, and when you remove all the uncertainty, that's the amount of information. In the particular case of this discrete set, is just a number of yes-no questions. We call it bits. Incidentally, at the very end, if I have time, I can tell you in which conversation of one Jew to another Jew in Berlin the word bit was first used. But now let's go from Boltzmann to Gibbs. Apparently, this is Boltzmann. It's just the logarithm of n. This formula, sorry. Now, we may say, but if I get an information by, let's say, messages, I open a Bible and I just read it. In my book, I have a home exercise, taking just the first line, Bereshit bara, and requiring the students compute the number of information in this letter. And particularly when I did it at Harvard, that most of them did not know Hebrew, but it does not matter. They see that there are different symbols, and this should be enough for sufficiently long text to estimate how much information the first sentence of Deuteronomy gives. So now let's say that if what all letters was used with the same probability, then every letter would give a logarithm of 26, which are letters plus space. And if word love would be just 4 times this. But in reality, we're now in a Gibbs situation, not in Boltzmann situation, because we know that different letters have different probabilities. Okay? And now, because we're talking about probabilities of frequencies, we may ask how much information we get on average. How you do average? You take a really very long book. It could be a telephone book, it could be a Bible book, and just look at all the letters which over there and ask what on average it gives. So you are treating the sequence with the length n. You take this n to infinity. And now we do know that a letter number I happens that many times, because we know that the total number of letters is n, and this is the frequency of this letter. Okay, so now when we take any book, we know how many times every letter happens. What we don't know in which order they happen. So now when every book is a particular choice of this order, only single choice of that number of orders that you can make out of n book letters. So you need to compute out of what number of possible orders are made this choice. So now we say, well, that's easy, because if we take out of n this number, it will be nw1 will be number of a letter A, nw2 will be number of a letter B. This is just the usual combinatorial formula. If you just don't remember, this is how many permutation between k object is just k factorial. Okay, so if you will, how many ways to distribute m objects, m being let's say letter A over n boxes, this is this combinatorial formula. Now we generalized it for this formula for out of n we take a product. Here I runs from 1 to 26, so there are different letters, and we take logarithm of it, and that will be our information. And we use Stirling formula when we take logarithm, and I don't want to go into this simple arithmetic. What we get here is the Gibbs entropy. So Gibbs entropy, or as we now call it Shannon entropy, is an average entropy per unit letter when we know frequencies. Okay, and in particularly, it immediately, when you compute frequencies of the letter, it immediately lowers the entropy from 4.7, which would be if they would be used with the same frequency, to 4.1. And what is even more interesting, and I won't go into this direction, I have the whole section in the book about it, is just to mention that you may now understand that frequencies of letters is not only things that we know about it. We also know about conditional probabilities. For example, in English, after Q always follows U. So if we know Q and we know that there is extra letters, this will be always U. There is no other way. So there are some other correlations, and when you compute all this correlation, you understand that entropy of English, and also there are some combinations which are impossible, is actually 0.14, 0.17. There are kind of people still working on it. It's a very interesting subject, statistical linguistics, and it's unbelievably alive. I mean, you would expect that all things were done, and of course, now large language model enormously helps. Artificial intelligence now making revolution in this field. And this illustrated, this ratio of 4.7 over 14, it illustrates that actually all the correlation between letters make the information per letter less. You actually don't need all the letters in a text to get the same message. You need approximately 1/3. And it was illustrated by this beautiful, it's actually a poster, and it's, if you Google it, it's actually part of a famous poem in America. So this was a really advertisement in a New York subway. It's 70 something. So let's read it together. If you can read this, there's nothing but this, you can get a good job with high pay. Can you guess advertisement for which job it was? It was real advertisement. People get hired out of it. Anybody guess? It's secretary. It's a good secretary is somebody who could really scratch things and then restore the whole message. Not necessarily stenography. Okay, and you know, back at 70s, secretary was a high-paid job. Okay, maybe now I'll say a few words about numbers, because this is another way which moves us now in this direction. So what we're now doing, I subtly switched you into encoding, right? So we understand that the same message could be encoded in a much, much shorter way, not using all the symbols. And in particularly, one unbelievably influential way of encoding was invented in Khwarezm, and I guess in Bukhara, in Samarkand, by a guy who was called Al-Khwarizmi. And this is the way to write numbers. You can generally encode numbers very simply. You can use just one symbol and repeat it as many times as the number is, right? So you want a 5, you just have five symbols. But this is very inefficient for encoding large numbers. And there are different, again, ways of subdividing. But what Al-Khwarizmi did is not only subdividing, also this idea that you can use few symbols, but the meaning of a symbol will be depending of its position. And so in particularly, when you write 2021, it's already an algorithm, which from Al-Khwarizmi, it's his name, It takes 2 multiplied by 1000, take 2 multiplies by 10 and plus 1. Okay, so this is already way of encoding which involves operational. And so from now on, what I'm trying to make even next step in generalization is saying that we started from industry, from engines, from very engineering question. Then we defined statistics which allowed us to justify this thermodynamic inequalities, a law. Then we defined information as a choice and uncertainty. It actually was the same statistical physics, just explained on the different language, was the same W logarithm W. And now I subtly came into a messages. And this is, again, maybe a very general, it's actually a way of looking, is treating everything as a communication. For example, I mean, this is an example how you treat box as a communication, which is essentially a very frequent joke. I mean, when I was in boxing, they were saying that communication by gestures is the usual way that boxers treat their interaction. But now you can look at, for example, at physical measurements. So you have a measuring device and you have a quantity that you measure. You can treat this process as a communication from the event B to the measurement A. You can treat memory retrieval as a communication. You can treat prediction as a communication. So you're doing something about something. And this very general framework allows you to treat many different things in the same essentially way. But now, instead of probabilities, you need to introduce a little bit more general thing, and this will be the last quantity that I define. After that, I will be using all this. And this is called conditional probability. So now I have a measurement result, and this is something about event. But they are not necessarily connected one-to-one. But generally, I have under a given result of measurement, the whole probability distribution of different events which happened over there. That could be actually independent on this. It could be a delta function at a given value, or it could be a spread distribution. So it's a more general framework. And this conditional probability, of course, if you multiply it by a probability of A, it would give you a joint probability of B and A. This is called a chain rule. So in a sense, if A and B would be independent, this would be just P of A times P of B. This is generalization for the fact that our measurements is dependent on B, but not necessarily give the whole information. Okay, so now we can define a conditional entropy of this is a probability distribution. So we can define its entropy. It's a conditional entropy of B under condition of A. Okay, and then we may ask how much information our measurement brought, and it brings us to the next step, which all practically all done already by Shannon, which is the last most important quantity which appears, and called mutual information. So when we ask what information was brought by a given message or measurement or whatever, we say before with the measurement, there was some probability of B, a priori probability, and it was the entropy, which is our measure of uncertainty about B. After the measurement, we have a new conditional probability, so our measure of uncertainty generally less. It's very many beautiful convexity theorems, which are, it's a beautiful mathematics which prove all this positivity, and surprisingly non-trivial. Kind of intuitively, it's kind of natural that, of course, conditional entropy is always smaller than unconditional entropy, and their difference is information. So that was uncertainty before, that's uncertainty after, the difference is, and it's really, when you write all this formula express, it's really symmetric, which means that the students find it hard to believe when I tell you them that there is an atom of impurity in a given crystal and you do X-ray. So there are like 10 to 23 positions for this atom. But your device has only 10 positions, right? So there is the entropy of your device is logarithm of 10. The entropy of impurity position is logarithm of 10 to 23. But if you're now asking how much, if I know the measuring device reading tells me about atom, as much as if I know the position of atom tells me about measuring device. It's symmetric with respect to A of B. And so it's a universal degree of correlation between A and B. And this is a very general framework. And I think these are most important things. And now you open any work on whatever, artificial intelligence, self-driving cars, black holes entropy, quantum computer, etc. What you find out is that they are using or entropy if they are on a basic level or mutual information. That's it. It's really, it took me some time to realize how powerful this two simple idea, one is W logarithm W, is the definition of S, and another is S of A plus S of B minus S of AB. These are two most important things, and they are really very, very workable. This is something which is called Venn diagram, and I want maybe just to have it. So if you look at S of AB, it's the entropy of their joint distribution, and this is S of A, and this is S of B, and this is their degree of correlation. It's a mutual information. Okay, and now what I really want to do, I want to show you examples, how it works, okay? Different things. And so what I would say is that starting from about 50s probably, it's just avalanche of applications, more or less using the same kind of simple formula, okay? So we start from life. What is life? And what life needs? And then you may say, okay, life needs energy and matter. Yeah, we need to eat, and it gives us atoms, which we use, and that also gives us energy. But of course, we're physicists, so we know that energy is conserved. As much energy as we got in, as much energy goes out. We are not getting more and more energetic with age. Actually, it's the other way around. But let's say on a short distance, and the same with matter. All the matter which comes into us comes out of us. We are, well, if we're fortunate, we have the same weight over the years, and we more or less have the same composition of atoms. So when we ask what is actually we need to, why we eat, why we absorb, or take a plant. Plant needs a solar energy, but it emits the same energy as a heat because it cannot consume energy, it cannot store energy, okay? And then you realize that what actually you need is information or negative entropy. At this point, what you realize, and this is kind of a new way of looking into usual life, that any life, when you look at it from the probabilistic viewpoint, is a very improbable configuration of atoms. We are in a thermal equilibrium not when we are dead. Long after we are dead, our atoms come into thermal equilibrium. So we are in a very low entropic state, each one of us and every plant. And to be in this state, you always need to get entropy out. You always, because otherwise you will be increasing your entropy in approaching the state of thermal equilibrium. And of course, our body and our mind do this in a very smart ways. And in particularly, if you ask how DNA works, again, from the viewpoint of the same Gibbs formula, so you ask, what is essentially a typical energy which binds bases into base pair into the DNA? You find out that it's just 10 times higher than temperature. I'm taking room temperature here, 20 Celsius, which means that the probability of error at such temperature, it's 10 to minus 4. It's exponent minus 10, which is essentially 10 to minus 4. This is totally little. I mean, we cannot live if we would be in thermal equilibrium and be behaving according to Gibbs. So what actually one does, and two people got Nobel Prize for it, this is already 70s, they say that what our body uses is kind of a Maxwell demon, which always does proofreading. It always checks. And for this, it needs a free energy. That's why this slide is actually what we need is a free energy to survive, and not an energy, is that you always need to check something against your pattern, and just by doing many such steps. So what essentially you are doing, you are replicating some very improbable configuration of atoms, and for this you need your energy source with entropy much less than the energy sink with which you emit. And at this point, usually some smart students ask, but what about plants? Plants get solar energy from a very hot sun, and they emit energy at our, again, room temperature. But temperature is in the denominator. So if the same amount of heat is obtained from sun at a very high temperature, it corresponds to a very low entropy. And when the same amount of heat, because energy is conserved, emit by a plant, and plant also warm, a little bit, but they're warm. And this is something which kind of students find surprising, that the sun is a very low entropy source of energy. And the chocolate is a very low entropy source of energy. It's 500 calories on 100 grams. Nature does not do it. You really need very good engineers to pack 500 calories into 100 grams. It's a very low entropic state. And when we eat it, what comes out of us is a very high entropic state, because what our extraction system. So now it also let you to look at this information from the information viewpoint, which is now a leading paradigm in biology. When I teach here information theory at Weizmann, there are maybe 20% people are biologists, well, kind of system biologists, because logarithms, and some biologists are still scared of logarithms, but a lot of them. So now when you look at biology, of which central idea is evolution, then you understand that what they taught me at school, that evolution is survival of the fittest, is just wrong. It's no survival of the fittest. No one survives. All die. Fittest, non-fittest, what survives are information in genes. So now when you look at evolution, and this is now a working mechanism, working theory to look at it, that evolution is a more and more efficient encoding about environment, information about environment in the genes of a population of this environment. So when you look at the farmer and say what he does by this selection, what he does, it encodes information about environment in the genes of its cow. Okay? So this is just one way to look at this. And now I want to switch from another equally probably important way of keeping us alive and processing information. It's a brain. So we talk not much, but a little bit about genes. There are two most important things, of course, genome and brain. So how brain works? Is all this Gibbs entropy, mutual information, all this nice logarithm have any relation to what really works with information, which is brain? And that was in 50s, and it's unbelievably beautiful works. I just physical pleasure reading their papers. I mean, it's 70 years ago. So what people did, there are many people, but it usually goes by Hyman-Hicks law. There were two different people. Hyman and Hicks was even in different countries. So what they did, they showed people different symbols, numbers usually, and a person need to say what numbers. I mean, it was about recognizing a symbol. And what they measured choice reaction time. So you need to think few split seconds to recognize the symbol. And so you can now take these symbols 1 out of 10, or you can take 1 out of 100, and you can take 1 out of 1,000. Again, you can play it with numbers. And they noticed that the time it takes to on average, of course, to recognize the symbol goes logarithmically with the number of possible choices. So if you take symbols 1 out of 1,000, there will be logarithmically larger than 1 out of 10. And of course, it immediately means that our brain does it by subdividing. because logarithm means that we turn a product into a sum. So we kind of first recognize if this a double-digit number, and then we choose out of double-digit number. We don't choose other three-digit numbers, for example, out of it. Incidentally, if you do the same with a restaurant menu, then if restaurant menu is ordered into entries, desserts, etc., then again it's logarithmically grows with the length of dessert. But if it's unordered, you can just put all this, then it's linearly. So as you increase the list, the time to find the what you need is linearly growing. But if it's structured, it's logarithmic. And then now you may do things, namely, as the same game. You always start from Boltzmann and then go to Gibbs. So now assume that you show all numbers with different frequencies. The brain does not know it. A person sits and you show different numbers, but for sufficiently long time. Our brain is unbelievably effective in recognizing the pattern. After a while, this time which takes to recognize a symbol goes down and then saturates on some level. And this average response time decreases proportional to the entropy. Because if your frequencies are different, then your Gibbs entropy is lower than your Boltzmann entropy, and your response time proportionally is lower. And the true beauty in these experiments was when they turned the tables. I find this really brilliant. Let's prescribe the time. Namely, that every person needs to answer in 3 seconds or in 5 seconds, depending on the complexity. You just have a bomb and the person needs to give an answer no matter what. And so it means that now the time is fixed and you can change this length of time. So what you measure to compare with this length of time? Any guess? So we suspect that the time is somehow related to the recognition of the pattern. But now the time is prescribed. So when you change time, what changes is the number of errors. As you make time longer, the number of errors goes down. So now you have a set of true numbers and a set of your answers, and they aren't the same. It's a measurement which has some information about what was shown on the screen, but not perfect information, right? So you use the same framework which gave us mutual information. Namely, you measure the probabilities of input, which is what on the screen, and output, it's what a person gives for it, and making more errors means lowering mutual information. And again, you experimentally show that this is the way our brain works. Its reaction time, it takes some time to learn the patterns, but it's surprisingly fast. And those are this picture in logarithmic. So this is really, I find it's just brilliant. And maybe last thing about perception, well, not maybe the last, let's see. So it's about how would you really get this information from your eye to your brain. And this was another brilliant work. It's already at 80s, and I'll probably skip a lot of things. So what is really here needed is a response time, a response function. So for example, your eye reacts on a contrast. It could be large contrast. Here is input. This could be small contrast or large contrast. But let's say you have 3 levels of response. Like you say, this is low. So you need to choose which function, response function. Will it be linear? Namely that linearly as your level of contrast increases, then you switch into next level. Or it could be concave, or it could be convex. For example, our ear does logarithm. It dumps strong sound and it amplifies low ones, right? At this point, I usually ask students why we have 2 eyes, 2 ears, which they easily answer, and then I ask them why we have 2 nostrils, they get into a stupor. When I taught this at NYU, one professor, also professors come there, told me that the most interesting thing that I learned in my course is why we have two nostrils. And I won't tell you because I don't have time, so you may ask me at the end. So what now was shown that the curve which was chosen actually is this one. It's actually your on it's a beautiful work of Laughlin. It's 1981. What he did, he took a fly and measured this response function. Namely, they were shown this fly, which were probably in pain but alive, different contrast, and they measured electric signals in the neuron which brought information. And what then they took camera, went to the swamp where this fly lives, and did this, namely recorded contrast in its natural environment and plotted the probability distribution of different contrast. And then they show that the response function is actually integral of this function. And I won't go into the detail, but it essentially tells you that you want to use all levels of your response with the same probability, namely by this transformation of response function, you take this probability distribution into a flat distribution which has maximal entropy. Of two normalized, of any among all normalized distribution in a finite interval, a uniform Boltzmann distribution has maximal entropy. So Laughlin experiment, there are no fitting parameters here. Look at this curve. No fitting parameters. You measure something on a swamp, you measure something in the lab, and that's a fitting. So this is just shows you the power, and this is probably the first real application of information to the data in the thing. And now I have last 10 minutes, and probably the last thing I'll tell you is about much more complicated things, is how the signal from the eye is actually get into the brain. How we, and this is now a problem of perception. The most simple thing, and which many people still believe, even though it's manifestly wrong, is that it like this. You don't know what's going on, then light hits your retina, retina sends electric signals, the signal comes to the brain, and brain decides, aha, that's my life, or that's something else. Actually, Helmholtz already 150 years ago suggested a totally alternative idea, which is now more or less a leading thing, is that perception as an unconscious inference, namely that our brain always predict. He never ever measures anything or get any signal. He get always the difference between its prediction and what is simple. Because the brain actually directs your eyes to see this or to not see this. And this was known actually since probably 15th century. Italians discovered the very beautiful phenomenon, which was then forgotten for quite a long time, which is called binocular rivalry. So you can put a thing in between your eyes and show here something red and here show something blue. What you would expect? You have your eyes getting two different signals, sending it, and there are many, many thousands of neurons carrying them over there. So you would expect that there will be some kind of a mixture, blue-white mixture. Well, it's a mixture, but in time, not in space. At any moment of time, your brain sees one color, which means that brain decides which signal to accept and which signal to refuse. You can do priming, namely you can show more red and then he will be seeing almost always red. If there won't be no priming, that sometimes is randomly switches into blue. But with priming, and this is something which clearly tells you that you see what you really are prepared to see. But you also look into something in which you are prepared to look. I think this is maybe the greatest discovery of well, it's going back to Helmholtz, but now we have a lot of empirical information about it. Okay, so this is essentially what is now called active inference. And again, in my book, I have a section on it, but there is a whole book. it's beautiful but almost unreadable. It is that sick of the guy who actually gets this theory. And of course, it's based on free energy. It tells you how your brain minimizes some kind of free energy. And it tells the following things, that the brain always predicts what it expects to see. Its prediction is based on its previous experience. And it's very heavily skewed towards expecting what was before. Because what our brain does, it survives. It's its main work that it does. So for survival, you survive up to this point. This is the most important information that our brain has, right? And so it's heavily skewed towards the previous experience, but then it gets some mismatch between what he expected and what is obtained. So you need to negotiate this difference between what you expected, and you want to more or less believe this because, I mean, if you fish, you want to stay in the water, right? So you really want to have the same experiences that you had before. But on the other hand, you really need to account for this kind of a mismatch. Every time there is a mismatch, which means there are two terms, free energy negotiate this extremum of this functional. It's always E minus TS. Okay, and so the new theory of a brain, which is called active inference theory, is just classical statistical physics based on the notion of free energy, and it's really kind of for physicists. Well, of course, as physicists did it now, and this is one example of how prediction works. Much more ambitious thing, which is still very, very controversial, is can we use this thing to measure conscience? It's a very practical question. Doctors need to decide whether you switch off, whether this person is already a vegetable or not. How you actually, and there is no response. There are many, many situations in which the brain is still alive, and how you really try to measure the degree of a collective state. Because when you're a vegetable, the brain still works, it kind of rules the, I mean, you breathe, blood flows, just everything works. And the idea is, it's called integrated theory of conscience. And again, it could be in 20 years, people say that this is the greatest discovery. I don't know, it's still controversial, but I find it very, very interesting. It's they measure mutual information between different parts of the brain. What they noticed is that there is one state in which we definitely know that conscience does not exist. And when we go into operational room under general sedation, everyone who passed through it knows that when you wake up after it, there is no feeling of time passed. When you go to sleep and you wake up, you have a feeling that something, you don't know how much. But when you go into general sedation, so they really now try to compare a brain in its state, which exists, with the state of a general sedation. And the difference is the mutual information between different parts of the brain. Maybe one last example of the same use of free energy into model things is the thing which are related to artificial intelligence. I can talk much more about artificial intelligence, but I can just maybe mention one thing. For example, you are trying to do something like self-driving car or whatever. So you get your visual camera, it gets huge amount of information. You need to make a very kind of finite choice decision, like left, right, slow, faster, right? So you need to encode this 10 to 5. This is what our brain actually does. We get 10 to 5 bits per second in our retina, and we get about 10 bits per second, maybe 50, into the brain. So you need to squeeze all this information, which is encoding. Okay, so you want to encode as little as possible into your decision-making algorithm. So you take this A, which is your camera data, B is your street, but you also try to get mutual information between B and C as large as possible. So you want to minimize this, encode as little as possible, because most of visual information is totally redundant. Every pixel is more or less like its neighbor. But you really want to keep this. And it's again kind of a free energy thing, which you need to minimize something which is functional made of two terms. Okay, and maybe last thing that I want to mention, and it's totally different domain, it just shows how wide is this. Is that I mentioned about black holes. So a person who worked in Jerusalem, but this discovery he made when he was still a PhD student in Princeton with John Wheeler is a Bekenstein, and Bekenstein answered a very important question, which stays answered how much information could be in a given region of space. Is there any bound on it? And surprisingly, it was found that if you have a radius r in the given, then there is an amount of entropy that you can put. It behaves surprisingly, not as a volume. This bound is not r cubed, it's r squared. It behaves like area. And this, because it's r squared, it divided by something which has a dimensionality of a square distance, which is Planck constant. And Planck constant is the only quantity which says all three fundamental constants that we have in physics, which is speed of light, gravity constant, and h bar. And this is the idea, again, it's an expression of religious belief, but now not in energy, but in the second law of thermodynamics, that if something goes out of our world, and the only way out is into the black hole, then the entropy must only increase and could not decrease. And from this, Bekenstein derives this bound, which is, again, one of the most important recent results. So at this point, I want to finish. I'm speaking for 56 minutes. So this book is devoted to Leo Szilard and John Wheeler. And John Wheeler was a PhD advisor of Bekenstein, also of Richard Feynman, for this matter. And Leo Szilard was a guy who started all this. He was a student at Berlin University who did not like the problem given by his advisor, von Laue. And so he met younger professor, Albert Einstein, in the corridor and says that, I want to write my dissertation on Maxwell Demon. And Einstein said, well, that's nonsense, etc. And then he asked for another 5 minutes. He explained in this conversation, the word bit was first born. And the dissertation of Szilard is kind of official birth of information theory as a discipline. Okay, so I devote my book to these things, to these two people, and I end up with a quote from a Wheeler, which says that all things physical are information theoretic in origin, and we are still very early in the process of understanding it. Thank you for your attention. Questions?
Thank you very much, Gregory. Mikhail, you have a question?
כן.
מיכאל קרייבנוב, מובילאיי.
כן. קודם כל מאוד, גרגורי, קודם כל מאוד מעניין, וזה גם איכשהו מחזיר אותי, אני גם פעם למדתי כימיה פיזיקלית באוניברסיטת מוסקבה, אבל אחר כך דוקטורט במכון ויצמן בביופיזיקה, ועכשיו ברכבים אוטונומיים. אבל אני בתור רק לשקף את התחושה יש הבדל גדול בין חלק ראשון של ההרצאה, ששם זה באמת יסודות גדולות, נכון גרגורי, יסודות, אבל הם הגבלות, כן? הגבלות, כן, של חוקי תרמודינמיקה.
תמיד הגבלות. תרמודינמיקה עושה רק הגבלות, נכון.
הגבלות, נכון. אבל לפלא בחלק שני, לפחות 16 שקפים ראשונים, זה היה בסיס, והם הגבלות, ואנחנו פחות מתעסקים בהם יום יום. נגיד, אפילו בעבודות מאוד מעניינות שאתה הצגת על המוח, זה כל כך רחוק משיווי משקל, וכל כך, זה כבר תרמודינמיקה אירוורסיבילית, וכל כך שבעצם חוקים, זאת אומרת, אתה עדיין יש הגבלות, אבל למעשה אתה לא מגיע להם, וגם מה שהזכרת בסוף תומך בזה, כי לאו סילרד, אני הייתי, כשהייתי דוקטורנט במכון ויצמן, קראתי מאמרים שלו על מקסוול דימון, ועם כל ההגבלות עדיין יש שם המון שאלות מעניינות, והיום, אז מה שאני רוצה להגיד, שהיום בדברים מעניינים שקורים היום, שזה גם מוח וגם AI, זה לפלא הגבלות משחקות רק חלק קטן, זה נכון?
נכון, אבל, okay, let me explain this. This is, first of all, maybe the most important thing that, at least personally, what happened in my life, is understanding that all this not about thermal equilibrium. It's a totally general principle. It was actually formulated, what we call maximum of entropy. When I was a student, we always believed that it's about thermal equilibrium. It's nonsense. Already my students know that it's nonsense. It's formulated by James already 50 years ago, but it's very slowly gets into it. It's called the truth and nothing but the truth. So in a sense, when you have any data, and it's not necessarily about equilibrium, your state, your guess about probability distribution realizes maximum of entropy under a given data. So now what we apply all these things is to totally and generally non-equilibrium system. What we learn from Szilard essentially is that information and heat and energy comes on the equal footing. And that is something which allows you to go beyond the usual thermodynamic inequalities, because usual thermodynamic inequalities do not include information. If you have information, your entropy is less. So in this sense, I would say which started, and it's still in many places that people learn it in this way, which is very restricted about thermal equilibrium. No, it's a very powerful framework. For example, Ising's theory of a brain, done by Bill Balik and other things, it treats brain as equilibrium Ising model of spins. But of course, it's not in thermal equilibrium, we are alive. But the statistics which you obtained, it's just because you measure the probability of any neuron firing is like spin up, and the probability of two neurons firing together. It's like two spins correlation. That's it. It's equilibrium Ising model, even though it describes non-equilibrium physical system, because it's a maximal entropy under given data. So it's a very general framework. Other questions?
Loma? You have a question?
לא, לא.
Okay.
טוב, אני יכול לשאול עוד שאלה, אבל רציתי כבר יותר קונקרטית, אבל לא רוצה, אולי אחרים רוצים גם.
Gregory, you mentioned two nostrils of a person. Can you elaborate on this?
Guess. Guys, any guess why we have two nostrils? We have two ears to hear the direction, right? We have two eyes to know the distance. Why we need two nostrils?
בדרך כלל זה redundancy, זה לעשות עוד משהו שאם אחד נפגע אז שני נשאר.
Why don't we have four legs? I mean, trust me, when everyone. Because not. Because our nose has two functions, not one, which is evident. It smells and it breathes. And even when it smells it's actually some kind of large molecules and receptors which catch it, but it catches differently. So our two nostrils always work differently. One makes a faster flow of air, and it's mostly for breathing, even though some receptors actually get it from fast flow. And another nostril is slower, and they switch one to another. It's a very recent discovery, actually. And this is why it's so difficult when you are when you have a cold, right? So then even one nostril is blocked and your system totally goes astray. So this the message is that there's two nostrils because of two functions, breathing and smelling. Any other questions?
טוב, אני אמשיך אז עם שאלה שלי, ישוע, בסדר? כן?
אוקיי.
כן. אז אני כמוך אמרתי, כן, שאני כמוך למדתי קודם כל כימיה פיזיקלית וכן, כימיה תיאורטית, ואחר כך זזתי לכיוון ביופיזיקה, ממברנות וחיידקים. אני קצת נפגעתי ממה שאתה אמרת שאין שום survival of the fittest. למה? כי אני בעצמי עשיתי ניסויים עם חיידקים. אני גידלתי חיידקים בצלחת פטרי, הוספתי אנטיביוטיקה.
They all died. כולם מתו, מה להגיד?
בסוף כולם מתו, אבל בהתחלה, וכשאני הוספתי אנטיביוטיקה לאגר, אלו שהסתגלו ניצחו. אמנם, אני לא אומר, אבל אי אפשר להגיד שאין כאן תופעה מסוימת של הישרדות.
מיכאל, of course זה היה בדיחה, כן. יש אלה שנשרדים קצת יותר.
כן, זה יכול להיות, אם היית אומר שהם באמת לא פיתחו את הגנים חדשים, אלא יתקלקל משהו ואז הם שרדו, זה יכול להיות, אבל זה נושא אחר מעניין. אוקיי, טוב. אז...
אוקיי.
עוד שאלות?
דוד? יש שאלות? רצית לשאול משהו? טוב.
טוב, רגע, יש לי עוד שאלה אחרונה עם בינה מלאכותית, AI, כן? איפה הגבלות תרמודינמיקה, מה שהם מתקרבים לאיזה הגבלה או לא? התפתחות של בינה מלאכותית ו-AI agents. איפה אתה משתמש שם בתרמודינמיקה?
Thermodynamics is a phenomenology which you use fundamental symmetries or conservation laws to impose some restriction. And it essentially works on any level because what we have started by imposing restriction on engines, how much we can get work out of a given scene. Then we ask how many information we can convey by a given number of sequence. So it's the same formula, just the same logarithm. We just use it not for work, but for communication. Then we ask the same things about perception. That's what we are doing now. How really we are doing perception. And at some point, I believe that this active inference, we're starting to doing things about emotions, for example. But it will be still the same things. That will be about uncertainty. Everything I told, let me return to the first slide. Uncertainty. We need to measure uncertainty at any given situation, and for a very different system, it's a very different ways of uncertainty, and in a very different restriction on this uncertainty. But the instrument is the same. Measure how much we don't know, what are the choices, and what are the relative probabilities. Very similar mechanism, and very simple technically.
אבל אם אני נגיד הייתי שולח את הבת שלי ללמוד על ה-emotions, על התחושות וכל זה, אז אולי במקום תרמודינמיקה צריך לשלוח אותה ללמוד פסיכולוגיה, כי אז היא תיכנס לעובי הקורה, כן, ולא על ההגבלות רחוקות, כי נגיד אם אני רוצה ללמוד על הפחד או על השמחה, אז מה העניין של uncertainties כאן, על אי ודאות? גרגורי, איפה זה? קודם כל אני צריך ללמוד מה זה פחד וממה אני מפחד ולא?
I don't believe in psychology as science, incidentally. I think it's pseudoscience, and I do believe in measurements. And now people measure things, start to measure things. For example, how we know that our brain really processes things? Because processing is a nonlinear process. It produces different frequencies, okay? So nonlinear process always make combinatorial frequencies. What I do believe that the present view of what our emotion is totally wrong. Our emotion is something very plastic and very learnable. And the moment you start understanding active inference, I mean, ask how your brain actually, I mean, look, it's a bunch of neurons in a black box. What it can do, obtain electric signals and send it back. And signals which come to there is no marks. This is from your grandmother or this is from your liver. It just learns and creates some models. And it can create very different models. We're in a very, very big surprises here. So, I don't know, maybe there is a good thing to learn psychology just to know the terminology over there. But what I would, somebody who want to understand what is fear or what is love or what other emotions is to learn information theory. And first of all, learn logarithm, because the pity of that many people who really work in this, I mean, they don't know Bayes formula, okay? And so they do nonsense. Well, that was my personal opinion.
Okay. Gregory, I want to ask some provocative question about telepathy. Maybe you know, in 1970s or something like this, there was a Russian book by somebody called
I don't know.
Kogan.
I know nothing about telepathy actually, so I'm the last person to ask about subject which I know nothing. Could exist, could be not exist. I don't know.
The book, which is still used in some Russian universities, is called The Applied Theory of Information. And there is a chapter on telepathy there.
I learned my information theory from Shannon. I remember back in Novosibirsk, I remember going, because we don't have this transactions of electrical engineering society. So I went through the forest and I found this paper by Shannon, mathematical theory of communication. I was in my third year. I remember that was kind of world changed totally. So this is how I learned. And then of course James changed a lot in my attitude. Yeah. But it's all
וספר של אחים יגלום, כן, על השנון, שווה ללמוד היום או שזה כבד וישר?
תמיד. כל יגלום, כל ספר של כל יגלום שווה לקרוא. היו אחים יגלום.
כן, כן, הם היו אחים וזה ספר קלאסי, נכון?
כן, כן, תמיד, בטח. אני גם קראתי את הספר. אוקיי, ישוע, בסדר.
אוקיי.
תודה רבה.
עוד שאלות?
תודה לכולם, כן.
תודה רבה, גרגורי.
תודה רבה.
מאוד מעניין. תודה.
תודה רבה. כל טוב.
תודה רבה. תודה רבה.